Okay, good. So today's material is on alternate light sources. And so we're going to be looking at other ways to collect evidence. And one of the ways to collect evidence is first you have to find it, okay? We talked about wet chemistry methods for large samples and then the sampling plan for making the lab samples and so on. But you have to be able to find the evidence, and alternate light sources is one way to do that. We've looked at color, we've looked at different spectroscopic techniques, and then you have different ASTM standards for different colors. But when we're looking at alternate light sources, we're looking at ways to change the contrast of the scene. So we're looking for evidence that is not easily seen with just your regular eye. So we use color a lot of times for that. Here's sort of this ASTM analysis flowchart. And of course we have infrared and we have electron microscopy and so on. But then down here under dyes, we have alternate light. And then under the microspectroscopy, also spectroscopy through the microscope, we can use UV vis and Raman, and those are going to use, again, UV light. Infrared is an alternate light source, if you will, and then so is Raman. We're using lasers to look at the molecular vibrational spectrum. And so we can do spectroscopy, not just in the regular instrumental methods like you're used to, go to the UV vis spectrometer, make your dilutions and so on, but we can actually do spectroscopy through microscopes. We can do even infrared spectroscopy through microscopes. Now I have one of those spectrometers upstairs with an infrared microscope hooked to it. So you can look at a sample and then you can flip over to infrared mode and you can get an infrared spectrum through the microscope objective. So it's pretty slick. It's a little tricky because glass will absorb infrared light. And so your optics either have to be salt or mirrors. And so the objective doesn't look like a regular microscope objective. It looks more like a telescope, which uses a Cassegrain optical system, sort of these nested parabolic reflectors, and you shoot the IR through those. And so you can still get like a 20x objective, but using mirrors. So now using alternate light source, sometimes you can see through things, and this is pretty exciting. You can do near infrared illumination, and so here's a writing sample that was obliterated with a Sharpie, and you can look in the near infrared and you can see that there's a different type of ink underneath the Sharpie, and so you can reveal it. So that's a pretty dramatic example. So if you're going to obliterate writing, be sure to use exactly the same ink and pigments. So here's some examples of looking in a scene or dusting for fingerprints using alternate light sources. We'll get into exactly what they're doing with the green light and the orange glasses in a minute. But this is these are some different crime scene lights you see here. A lot of them are fiber optic, so you can carry the little output optics here, but then the power source and the lamp is back here in a box or plugged in. These are very bright, so these are probably laser sources. And laser sources, typically diode laser sources, don't generate nearly as much heat as like a tungsten lamp with filters. And so we're going to talk a lot about the different types of light sources that we have for crime scene analysis and for evidence analysis in the lab. So here's again a spectrum for common visible sources. The sun still has sort of like a black body radiator. It has a maximum wavelength right in the visible region at a certain temperature. You have tungsten lamps, which give you a lot more infrared. So it's really pretty crummy. About 4% of a tungsten lamp is visible. That's why we've been pushing so much to get away from tungsten filament lamps or incandescent lamps in lighting, because they're just so inefficient. Think about that. You're buying 100 joules of energy from the power company, and you're only getting 4 joules of light. So you're throwing away 96 joules that you paid for, okay? Now, they're pretty cheap. A joule's not much energy, but it adds up, okay? And lighting is it can be up to, between 5 and 9% of your household power costs. And so you know, if you lived in the dark the whole time, you might save 10% of your bill. But still, it is pretty wasteful. The mercury vapor lamps or the fluorescent lamps, those are like 15% efficient, and LEDs are 20% efficient. So these, if you're at the grocery store and you see that bright light coming out of the scanner, that's a barcode. Look at its profile. So it's a very narrow profile, and so that's what you get from a diode. And the laser makes it extremely bright. So at the given wavelength for that laser, it's going to be, you know, off scale. In fact, this has probably been filtered down. Now the mercury vapor lamp, we'll look at a crime light that is a mercury vapor crime light, and it has bright peaks. It has definitely peaks in the blue and in the green, and then it's excited mode. It's got some peaks in the red. And so that's why we still use mercury in these tube lights. So these tube lights above our heads have mercury vapor in them, which is toxic. Okay, so that's why we're careful whenever we change them out. We don't want to break them because you'll be exposed to mercury. Mostly it's a vapor only when it's being used. When it's cooled back down, there's not a lot of vapor in it. But still, you know, exposure, you don't want to be exposed to toxic substances. So why would we still use a toxic substance? I mean, we could use something that's less toxic. We have sodium vapor lamps, and sodium's not toxic. Have you seen a sodium vapor light? The old street lights were sodium vapor, and they were yellow. So they were just not very pleasing. And so this room, if this was lit by sodium lights, everything would be yellow. And it just, you know, it grates on you after a while. Okay, so we like bright white light, and since mercury vapor gives us an R, G, and a B, it appears to our eyes to be white light. Our eye thinks all the wavelengths are coming out of that, but it's really sharp atomic emissions in the blue and the green and the red. So there's different forensic light sources. The UV is useful for fluorescence, and we'll talk about that later on. We have metal halide lights. It's very sharp peaks. Again, mercury vapor, but you could also have the tungsten halogen lamps. And so the tungsten is the filament, and then the halogen is around the outside. And what it does is it provides a pressure blanket around that tungsten filament and allows it to get hotter. And so the hotter it is, the brighter it is. So you get more light in the visible region if you have a hotter filament. We can also have a gas lamp, a xenon lamp. It gives good UV and a flat response in the visible region. But it gives off, again, more heat than light, and so we get a lot of infrared energy out of it. And then we have LEDs, which are wavelength specific, and I brought a couple of LEDs to show today. You can buy these lights here. These are, you know, if you buy them in bulk, I think I bought a pack of 10 for my cleaning workshop, and they were like $2 a piece. And these are supposedly UV lights. They're not really strongly UV. You can kind of see purple light. So there's a lot of visible light coming in. It's not great. Did it die on me? Yeah, there it is. It's not a very bright light, and so it's not damaging my skin. You wouldn't want to do this with like a strong UV light. But what this is sold for is an alternate light source for detecting things around your house. You know what they use these for? Anybody? The pet urine. Okay, bodily fluids. So that's what we're talking about is alternate light sources. And so you can buy these on Amazon, and you look around your house, and you got a funny smell in the living room. You find it on the curtains. Your cat has sprayed the curtains. Okay, so then now you know where to spray the Febreze. Okay, and that's a good product actually, because it doesn't just cover the smell. It has an oxidant in it, a mild. I don't know what the oxidant is. It's probably a mild peroxide, but it'll destroy the organic compounds that cause the smell, and if there's bacteria too, it'll destroy that. So So these are LED lights, and they're really cheap. And you know, the brighter they are, and the more LEDs you have, the more expense. But still, in terms of comparing them to these xenon crime lights, they're much cheaper. They have exceptionally long life, and they give you more light than heat, so that's very nice. So here's the Xenon Arc Lamp spectrum. And so in this fluorescent excitation, we really want to have the short wavelengths, and we'll see later why that is. But you have this excitation region, and then you have the detection region, and you put on these various glasses to block the excitation light so that you can see the fluorescent light. So that's nice and flat, and then you have all of this infrared light that is essentially heat. So you've got to throw this away. Can be a problem. Because if your lamp is putting out so much heat, you got to do something with that heat. You don't want to have it in your hand. You're going to have a power supply with a fan. You're going to have to blow air past that light, and then they got hot air blowing all over the place. And anyway, I'm obviously a fan for LEDs because they don't generate as much heat. The nice thing about this light is it's all wavelengths, and so you can use filters to pick your wavelengths. Since it's pretty flat and the visible, you know, you could have a filter that passes this amount of light here, and so that would be your excitation filter. And so only this amount of light is hitting your sample. So you're getting this amount of light onto your sample. And then that can cause fluorescent compounds to fluoresce, and then you put a filter on your eyes that lets the visible light through that's coming from the fluorescence, and then you can detect it and see it. You can put that same filter on your camera, and you could collect it that way. So this would be the collection filter. It collects that fluorescent light. Here's the different manufacturers, so that you can see this in the notes when you look back at the video. Coherent is a laser manufacturer, Specs Fluorescence, I think. They make those really nice. They're like a LED light, but they're really big. They have a really bright illumination field. And so what this allows us to do is to find and visualize more evidence, and we need to look to see how we're using these different light sources to detect things. So here's some of the evidence categories that you can look at with alternate light sources. We looked at an example of obliterated writing, so that would be document examination. You can look for bodily fluids at the crime scene, shoe prints, and so on. What we're going to look at this morning is we're going to look at some of the skin cells and things that I've left on this drawing pad. Okay, and then I'm going to try to make a fingerprint. I brought some fluorescent fingerprint powder too, which we can use these alternate light sources, the fluorescent powder, to see. Some grease marks that I leave on this clean glass plate that I brought. So we'll see. So we can use absorption mode. So we can look for dark spots. And so if we have a light source at 415 that's going to be absorbed by red, bloody residue, then we can look for dark spots, and that would be using absorption mode. So we could enhance contrast against a colored background by changing the angle of incidence of light. Now that's a really good technique. Let's see if I can. Yeah, you can see it. Okay, grazing angle. I don't have a white light, but you can certainly see the particles here. So I'm looking at it with a grazing angle. Let me turn this camera on. Let's see. I don't know if you can see it. I'm trying to find out where. Maybe if you'll turn the lights out for me. Yeah, okay. So you see how the light is just grazing along the surface? and the dust really stands out. You can see dust particles here, right there. Let's see, right there. And then there's a fluorescent particle here. Just me picking up that fluorescent fingerprint powder, some of the little particles fell out of the lid and have hit my little tablet right here. And there's another one right here. Now, with my eye, I really can't see anything special on here. I mean, I can kind of see this particle here because I knew where it was. I've lost this one up here, so I really can't see it with my bare eye, but there it is. Okay. So even if you don't have a fluorescent sample or a UV light source, just a regular flashlight shining at a grazing angle across the surface, all your particles are going to leave shadows. And so you'll be able to see really small particles with a grazing angle. Are y'all okay with the lights off? We'll just leave it like this? Okay. And then we have fluorescence mode, and that's what we were using with this UV light and this fluorescent powder. Okay. So this does look like Rhodaman 6G. I don't know what fluorescent powder this is. It just says red. Okay. But that does look like the dye that we had in my graduate research where we use Rhodaman 6G, and it'll get everywhere. I mean, it doesn't take much to turn the whole lab floor pink. So whenever you spill it, it's not a good day. Okay. Here's again, looking with visible light, you may think something is completely obliterated. You look in the infrared, and you can see the writing behind the paint. So that's pretty slick. So again, this is a really powerful technique. Here's some more obliterated writing. This is using UV illumination. And so there was a fluorescent substance underneath this marked out region that you could see through the marking. And so those numbers were able to be seen underneath the redacted area. And then here's an interesting thing. So this might be a receipt that was turned in, and some of the numbers were erased. And you can see the rubber residue on the paper from the erasure, looking in the infrared. And so you can tell that was probably a 1, that was probably a 1, there's some fat number there, don't know what it is, that was probably a 1. So there's 3 1s in the thousands place, and then a couple of other numbers. And so that might give you a clue if you're short, if the drawer is short $3,000, they erased the journal entries and pocketed the money. So the journal matches the drawer. Okay, but somehow you figured out, I'm going to go back and check the journal. Yeah, we're missing some money here. So that's, again, some interesting use of illumination. Here's another one here, very specific. So here, 1400 was turned into 100. And they erased that part of the 4 and erased that 1. And you can see the rubber residue from the erasure. The main point of this alternate light source technique is to enhance contrast. So when you're looking at, like when I'm looking at this tablet, everything looks black to me because it's a black tablet. And I need contrast between the evidence and the background. So changing the evidence from the background, that's what we're talking about, contrast. We want the evidence to stand out. We can use different color filters. We can enhance the reds and enhance the blues by wearing different kind of glasses, putting different filters on our cameras. And so let's review PChem 1 a little bit and absorption and fluorescence. Remember the old Jablonski diagram, right? So you have the ground state here, and you have the excited state, and you pump the molecules up to the excited state, and then they can fluoresce down. We're really not going to be talking about phosphorescence because that's a slower time constant because you have the spin flip. We're just really talking about fluorescence. And let me draw this a little bit more accurately. Well, I got it pretty well done here. So the fluorescence starts with molecules in the ground state. So this arrow is long, or let me say high energy. Let me do that. And this is notice this arrow is smaller. It comes down and hits a level that's higher and excitation. And so this is low energy. So the excitation is always higher energy than the fluorescence. Okay, so high energy, short wavelength. And the fluorescence is low energy, long wavelength. There may be some overlap. Overlap maybe. Okay, there doesn't have to be. They might touch, but they don't have to overlap a lot. Okay, and so in order to use this particular spectrum to our advantage, we want to put a block here to separate the two. So this is the excitation light, and we want that to hit the sample. And then this is the emission. And so this is what we want to observe. Does that make sense? We're trying to observe only the fluorescent light. We do not want to see any of the excitation light. So ideally, we would know what wavelength we have for our source, and then we would have glasses that don't let any of that light through. So when I look at the room with my source on, the room's totally black. I don't see anything. That's the perfect situation. Then only thing I see in the whole room is something that fluoresces. So if there's anything that fluoresces, it's going to be seen. And that's the best contrast there is. It's not very safe, though, because standing around with black glasses on, walking around a crime scene, you're going to trip on something, you're going to hurt yourself. So it's never perfect, okay? But that's the idea, is you don't want to see any of the excitation light. You only want to detect the fluorescent light. And so to do that, we use filters, okay? We have an exciter filter, and so that might be the profile for a filter. And this one, because it has a cutoff here and a cutoff here, right around that 50% cutoff region. This is called a band pass. Because it passes a certain band of light. It has a center wavelength, and then some kind of width here. And then this one has an edge wavelength. So this is going to be the EW, edge wavelength. And then look at what's passed by this filter. So this, again, this is transmittance on the y-axis. So that's the light that's transmitted by this filter. And so that means this light is being transmitted through the filter. So what light is it passing? See, these wavelengths down here are the long wavelengths. And so this is called a long pass filter. EW equals, well, we'll say 510, okay, nanometers. So you tell the edge wavelength, that's what EW stands for, and then you tell which side of that edge wavelength is passing the light. So this is a long pass filter with an edge wavelength of 510. So every wavelength greater than 510 is going to be passed by this filter. Now, long wavelengths are also low energy, and so sometimes this is called a low pass filter. And low indicates energy. So low energy passing. And how do you keep those straight? Well, long is a distance, right? So whenever you see long or short, you're thinking wavelength. Whenever you see low or high, you're thinking energy. Okay, so long pass and low pass are the same thing. Okay, so this is how we set up the system for the fluorescence optical detection. We have a source. We might have a bandpass or a short pass filter. Let's see, I've got this. So we use an emission filter to select the illumination wavelengths. We'll call that a short pass. And that lets the short wavelengths hit our sample, which is going to excite the sample. And then our detection filter will block those illumination wavelengths. And so this will be a long pass filter. And that lets the fluorescent light through. And so only those fluorescent wavelengths are detected. So we can set this up. Let me try to put a filter on our lamp here. Let's go here. All right, so we have these yellow glasses. We're going to block the light. I need to clean them, it looks like. Okay. And now that particle stands out even better. Okay, and this one too. Oh, I've smudged it. Look at that. Made a mess. It's probably on my hands now too. There's another one. Okay. Now one thing I wanted to do was, I'm not really good at fingerprint investigation, but I'm going to try. Okay. I'm going to make a god-awful mess. so we'll see. My little tablet's going to be pink for the rest of the semester, I'm sure. Because this powder is so ridiculously fine. All right, so we have this plate. It's clean. There's nothing on it as far as I can tell. I cleaned it this morning. I'm going to do my famous, get lots of oil on it. I know that's gross, but okay. And okay, so that's not exactly a fingerprint, but we'll see what it looks like. Can you tell really what it is? You see a smudge there. Can't really tell. Okay. And got this glass fiber fingerprint brush. There we go. So I'm going to just get just a touch of this powder. I'm not even going to stick it in there. I'm just going to touch the lid. Okay. You don't want to smudge the image, right? So this really fine glass powder. Yeah, I'm starting to see it. Yeah, got it. Okay. What do I do with that? Okay, cover this up before I make a mess. Can you close that for me very carefully? All right, thank you. Set that right there. Okay, can you see what it looks like? Okay, not very good. Let me blow on it. Okay, can't really see it. Let me get the bright UV light here, and we'll cover our camera. See how bright that is? It looks like a baby's foot. You see it? See the baby's foot? I need 3 hands. Can you come hold the light somewhere? Just hold it right there. You see that? And I'll tilt it up. So I smudged it, but I can see my fingerprints on there too. This camera may not be the best. I blame it on the camera, not the technician. So maybe I can show it to you like this. Yeah. But you can see how bright that is with this UV light. And it really stands out. Without it, you just see, and that was just a greasy smudge on the glass. So again, that's giving us contrast. There we go. You can barely see it. You shine the light on it, it really stands out. I see from behind. Yeah, there we go. All right, so this. I used to, things you learn in high school, right? The little baby's foot. I used to put those on the chalkboard, and that and little smiley faces. I'd go up and sharpen my pencil in algebra, and I would put a smiley face on the chalkboard. And the teacher was doing his algebra lecture, and he looked over and saw the smiley face, and smudged on the chalkboard. This was before whiteboards, it was actually chalkboard. So he would reach over there and erase it. And so I was like, oh, he doesn't like that. So what do, right? I do more. And I was one of those kids for sure. And so then one day I came into class and he wasn't at his desk. And I was like, So I go over there to the board. I start doing the baby feet all over the board. It looked like a little kid had walked across the board. And I get almost to the whole board done, and I hear in the back, Mr. Williams. He was sitting in the back. And he said, you will erase the board after class for the rest of the year. I was like, okay. So anyway, that's as bad as I got. Maybe. I'm not telling you anymore. Okay. So let's look at the different filter types. We have absorption filters, which I was talking about. But we also have these type of interference filters, which are really made for the laser wavelengths. So interference filters are more complicated and obviously more expensive, but you really need them for if you're going to be using a laser light source. They tolerate more heat than an absorption filter, so they're really useful. But because of their cost, they're probably part of a larger package. So this is how an interference filter works. And like I said, it works best with a laser because with a laser you have a well-defined wavelength. So you have a laser coming in with a particular wavelength, and the interference part has this layer that's been deposited on the surface of the filter. And that layer has a particular thickness. It's some multiple of the wavelength of light plus a half. Okay, and what's the half about? Well, it goes into the filter and it hits. So follow the blue path. It goes in, it goes down, up. So that's one wavelength and a half. Okay, it comes down here and hits, and then it comes back. The reflected wavelength comes back, and then it's reflected in the green. And when it gets back to the front, it's out of phase with the original wavelength. And so then you have interference. And so it's destructive interference, and very little light leaks out on axis. Okay. Now you may say, well, how does this work? Because, energy is neither created nor destroyed, right? So where does that energy go? Well, it goes off at different angles. Because if we have light that's coming in at a different angle, then you're going to have constructive interference, and you'll have a big wave here and a big wave here, but very little wave on axis. And so that's how these work. The missing energy is sort of resonant at other angles. And so you can use layers kind of like a grating or a monochromator. So they make volume gratings instead of just reflective gratings where you have scratches on the surface. You can make a volume grating with layers, and then it'll pick angles at which that wavelength of light can be dispersed through that resonant structure. So this is kind of like a volume grating where it picks different angles for that wavelength. But on the straight angle, straight on axis, very little light goes through. So that would be a dark spot. If you were to look at all of the angles that come out of an interference filter, you would see rings, but the center of that emission would be really dark. So you just you illuminate with the center. You have optics that block these other angles, and so very little of the laser light comes through. Okay, absorption filters, they just have an absorption layer and any thickness. I mean, the thicker the layer, the less light comes out. And so all that energy is deposited in this absorption layer, and so this absorption layer can heat up. So since you've got an intense light source going into a filter, that filter is absorbing that light. The filters need to be cooled sometimes. Depends on the brightness of the light. And so this is that exponential decay, which is what we have for Beer's law. So the light just drops off exponentially. So here's some more on the different types of filters, where we talked about high and low pass filters and short and long pass filters. So here again we have a transmission spectrum. So transmission is on the y-axis. So when it's at 100, that's 100% of the light gets through. This would be in the visible region, dipping down a little bit into the near UV. We have that edge wavelength, which should be right at the 50% of maximum transmission. So the edge wavelength is not enough to tell us what kind of filter it is. So that's just where this edge is. You need to know if it's a low pass or a high pass or short pass or long pass. And so this is a short pass filter. So that means the short wavelengths are passed, which means the short wavelengths are transmitted. Okay. This is also called a high pass filter. Why am I calling it high? What's the high refer to? Yeah, so high energy is being passed. High energy and short wavelengths go together. This is the long pass filter. You have your edge wavelength here at about 550. And this, again, the long wavelengths are being passed. So long wavelength. And this is a low energy pass filter. And this is going to be the filter that you use for doing what? You have two options. You can use this as the illumination filter or as the observation filter. So what would this one typically be used for? Observation, because it's the long wavelength light that's fluoresced. And so we would use this on the camera. We would use this on our eyes. And then this is a band pass. So it's passing just a band of wavelengths. So you have a central wavelength here, and you need to know, so that here the central wavelength is not an edge, it's the middle, the maximum transition. And then you have this bandwidth that's passed. So you need a delta lambda here too. So the CW tells you the center wavelength, but then you need this bandwidth. If it's very narrow, it's called a notch filter. It's like a notch out of the spectrum. Okay. So this width right here would be given as probably a delta lambda. You could use this one for illumination. I guess you could use it for observation, but it's probably just going to be an illumination filter. We're giving it a particular color to enhance contrast. So here's one of the xenon light sources. It's kind of bulky compared to say an LED. It's got the lamp housing here. You've got a fan inside this housing. It's got the xenon gas lamp in there. This right here is pretty nice though. This has your filters built in. BUILT, okay, built-in filters. So there's a filter wheel in there, and it looks like you could probably put 4 or 5 filters in there. So you can just rotate them in front of the light. And so you could have, a short pass, a couple of different band passes. There really wouldn't need to be a long pass in there because that would be on your detection side. And then you need a power supply. So this is the power supply. Quite a bit more bulky than one of the crime lights, the LED crime lights. But here's some of its specifications. Here's the different goggles, and you have, here's the 4 long pass filters. You got a 62 millimeter diameter red and a couple of different orange camera filters that come with it. You've got 7 filters inside this filter wheel, so that's pretty nice. Okay. You can plug it in, or you can have a battery pack, etc. Here's the LED forensic light sources. Look how small they are compared to that Xenon crime light. So again, these look like pretty large flashlights, and they're a little bit more bulky. They're smaller than this water bottle, but not by much. Okay, so mainly for long life. They get pretty decent battery inside, and again, a big illumination area. So you can buy these different wavelengths, most of them in the blue or near infrared or near UV. So here's a picture of the different colors. You have green and green blue, blue and violet. Look how narrow their illumination is. So this is even better than what you would get out of a bandpass filter. It's more like a notch filter. And again, most of the light is being emitted in this narrow band, and so they're incredibly bright for the power that you put into them. They last longer, there's less maintenance. Again, more energy efficient than the incandescent or halogen lamps. They don't have to warm up, so they're stable over time. You turn it on and it's ready to go. It doesn't change over time. And they're pretty robust. You can drop them, and not bust it. They also don't have mercury or toxic gases. If you drop it, you're not going to break the filament. It doesn't produce any ozone or anything like that. No warm-up period, so they're really great. That could be a commercial for them. And then even brighter than LEDs is if you put that light-emitting diode in a resonant cavity and make a laser out of it. So these are incredibly bright. You can shine, again, this light is not that bright, and the farther I get away, the less effective it is, because it's not very bright. But a laser is going to send all of its power in a straight line with some, you defocus it a little bit. And so with one of these, I could stand pretty far back with my glasses on and see evidence. So I wouldn't have to walk over to a contaminated area. I could search better if I had a laser. It's just so much more bright. And so this that's where you would want one of these lasers. Now they have a beefier power supply. They're much more expensive, so you're going to need to plug them in, and so you don't want to carry this bulky thing around. And so I like this one here. It's got a fiber optic wheel on it. So you've got the laser and a power supply in here. You turn it on, little safety shut off, etc. And now the light goes through this fiber optic, and you've got this handheld optics basically. And you put your glasses on, you search around, you see the bodily fluids or what have you, and then you can start taking photographs. You put the same filter that you're wearing on your eyes, you put that on your camera, and so your camera gets what you see. Okay, and if it's still far away, again, you use a zoom lens to get in close. So that's the alternate light source. Are there any questions about any of these things? Okay, great. Well, we'll see you next time.